Okay, so for the last few lessons in Unit 1, we're going to move past gases and talk about some of the characteristics of liquids and solids. The first thing we want to cover in relation to that is this picture or graph of a phase diagram. So this is something that you'll want to be able to read and interpret. You can use phase diagrams to decide based on a certain pressure and a certain temperature what phase a substance will be in. So would it be liquid? Would it be solid? Would it be a little bit of both? And we'll talk about how to read these. So just to do a quick review, all right, hopefully you can match these up, but pause the video here, see if you can correctly identify these. But a solid should match up with having a definite shape, and it's not compressible. A liquid should match up with taking on the shape of its container, but also not being compressible and kind of staying confined to its container. Whereas our gases, those are the ones that have that awesome compressibility. They fill up everything, even going outside the container if they're able to get there. All right. So when dealing with a phase change, there are some important concepts to keep in mind. As phase changes, the energy of the substance is either going to be increasing or decreasing. All right, and when we're talking about that, we're talking kinetic energy. Remind me, what is kinetic energy related to? A couple things you might say here would be like it's related to temperature, it's related to the motion of the molecules. All right. So if you think about it, as we get into a gas, gases can move around a lot, right? So they have high kinetic energy, high motion, all right? Their temperatures are also going to be higher. All right? On the flip side, if you go to the other end where you are releasing energy, losing that energy, molecules are going to have less kinetic energy, they're going to move slower, all right, and generally your temperatures are going to be lower. All right, this kind of, you can also think of this as makes sense because, if we talk about, say, boiling point or freezing point, we know boiling points are always higher than freezing points. All right. Now, another concept that you've got to wrap your head around related to phase changes is the role of intermolecular forces. So think about that one. See if you can remember, or if you have any recollection, or if you can even kind of take this word and break it apart into what it might mean. All right. But intermolecular forces are attractions between neighboring molecules. All right. So if you remember, a unique quality of water is that water kind of attracts itself, neighboring molecules. So water has high intermolecular forces, which gives it some of its unique properties. All right. You can also think of it as like the intermolecular forces are going to be something that works against kinetic energy. It's an opposing force to the kinetic energy. All right, so if something has high intermolecular forces, it's going to want to be down at the solid end. All right, so high intermolecular forces is going to be associated with keeping something more solid. Low intermolecular forces is going to be associated with keeping something gaseous. All right, so these are two things that kind of work together to decide what state a substance is in. So, phase diagrams will look something like this. Every different substance is going to have a different phase diagram. All right? Water is going to have a phase diagram where, its liquid portion is much bigger because water it has a much larger range where it tends to be liquid. Whereas say something like table salt is going to have a phase diagram where at most pressures and temperatures it's solid. All right, so this will shift depending on the substance you're working with, but they're all going to have some key similarities. All right. First off, your axes are going to be the same. Whenever you have a pressure and temperature, a phase diagram, you're going to have temperature on your x-axis, and you're going to have pressure on your y-axis. All right? So the temperature one is something you're probably more familiar with. If you kind of just look as you go across here, you kind of go temperature, as temperature increases, you go from solid to liquid to gas. All right? The tricky thing is that this diagram also shows how if you change pressure, that causes stuff to be a little bit different. All right? So really, this shows you the combination of making pressure changes and temperature changes and how that will affect the state of your substance. So a couple of just pieces you want to make sure you're familiar with the name of is these list of words that I have on the right here. All right, so the first thing is your fusion curve. That is this line here. So this is the line, and if you trace this line, this is the combination of pressures and temperatures that have a substance switching between solid and liquid state. All right, we call that fusion. All right, they're either fusing, freezing to become solid, or they are melting to become liquid. All right, so this is where freezing and melting happens. All right, whereas your vaporization curve, all right, that's right here. This is the combinations of temperatures and pressures that boiling and condensing will happen. All right, or another word for boiling is vaporization, and that's why we call it the vaporization curve. All right, so vaporization, boiling, whoops. Versus condensing curve. All right, and the last thing is some substances have the ability to skip the liquid phase, and we call that sublimation or deposition. All right, and that's this sublimation curve. All right, so this is where things can go straight from gas to solid or from solid to gas. All right, completely skipping liquid. Oops. All right, so this is something where, like, if this was a water phase diagram, there'd be almost no sublimation curve. All right, it would be very much the green and the blue curves. Now, a couple of key points, all right, are going to be where these intersect. So the first one you want to know is your triple point, all right, and that is right here. That's where all three of those intersect at that specific temperature and pressure. You actually would consider your substance to be in all three states simultaneously. So solid, liquid, and gas. All right. Critical point is another one of those, and this is where when you go higher than this temperature or higher than this pressure, you can't tell the difference between it being a liquid or a gas. All right, so that you can think of that as like the intersection of liquid and gas. So these are special points where you have just very odd kind of conditions of what's going on with your phases. So these are good terms to know, good things to be able to kind of understand related to a phase diagram. So how to use a phase diagram. You're going to get questions kind of like this. For example, in what phase is substance X at a pressure of 100 kPa and 10 degrees Celsius? All right, so you're always gonna need to be given a pressure and a temperature, and what you do is just treat it like that's your X and Y value. Figure out where that point would be. All right, so if I go over to 10 degrees Celsius, all right, and I want to be at 100 kPa, if I find where those intersect, that is where my substance would be. All right, which means that at this temperature and pressure, substance X would be a solid. All right. How about 50 degrees and 400 kPa? So let's look at that one. So here's 50. Here's 400. If I look at where those intersect, it's going to intersect in this liquid quadrant. All right. Now here's one. So let's look at 100 kPa and 28 degrees. So I'm going to continue my 100 over. And then 28, I'm going to say that's probably about here. Oh, that seems to happen on my line. All right, so this is where we're going to be on that sublimation curve. All right, so this is on the sublimation curve. So we are between solid and liquid. We're in that transition phase. Or sorry, solid and gas, because it's sublimation. All right, because it's right on the edge between these two. All right, so we're kind of in both when we're along that red line. Okay,